To see how the stack is used for local variables, I have this program that in main I print the address of a local variable A, and then I call f and g. Each of f and g has a variable, either a double or a character, and it prints out the address of those variables. So I've got that program over here as main.c, and if I compile it and run it, then what we see is the address of A and M is at this address. You can see it ends in ff3c. And then while main is still running, it calls f. F has a variable b that's in ff18. This number is less than that one because M called f. It pushed a new variable onto the stack. F returns, and then M calls g again, and g's local variable you can see is at this address, which is in between the two addresses of A and B. So what has happened is that B has gone away, and then we put something smaller, C is just a character, in its place, and so it lives a little bit higher than B did, but well below A still. Now this is not the kind of thing that C actually guarantees. This is just showing you how C programs tend to work, and since it's not guaranteed, naturally it's the kind of thing that we might see influenced by optimization. So if I try compiling this with optimization, and I run it again, we don't see that same pattern at all. We see A is at some address, and then the address B in F actually lives deeper in the stack. FFD8 is bigger than D4. How can that be? Well, it's because given license to optimize, the compiler says, I see F, I see G, I can just take these variables and printfs and put it all in main. There ends up being only one function with no F and G, and they all live in the same function main, and the compiler just happens to order A and B different than they would be if the functions were not inline. We could tell GCC not to do that. This is not standard C, and you almost never want to do this, but if for some reason you don't want it to inline, you can say attribute no inline. So I will use that for both of these functions. Try again. And run again, and now we're back to the kind of picture that we had before, where the variable in main has a certain address, and B and C have deeper addresses. Let's try this. Let's use OG, which is about the same in this case, and include debugging information, and use GDB to watch things. So I'm going to set a breakpoint at the function f, so break f or just bf, and then I will run. You can see the program got as far as printing the address of A. It's inside of f. If we go to the next statement, then it's about to print the address of B. We can look at that ourselves before it gets printed out. So the value it's going to print out is hex 7 with lots of f's, E0B8, that is below EDC. We can also, in here, in GDB, use $RSP to print out the value of the register. And we see that the register's value currently ends in E0B0, which is below E0B8. That means there's a little bit more on the stack beyond B. Just for your information, if you want to see all the registers, you can do info registers and they'll all print out. And you can see RSP here is the one we just looked at with the $sign notation. So again, that's where B was. I'm going to break at G as we continue. So now we're in G. We can look at the address of variable C in G. We can compare that to the stack pointer. RSP in this point is greater than C, and that's because we haven't actually created C. I didn't step to the next line yet. But if you do, you'll get the result you expect. We could also disassemble F, and let me show you that here. If we disassemble F, let's run again and have it break in F. Go to that print statement. If I run disassembly while I'm inside of F, it disassembles F. And you can see that this load effective address, 8RSP, actually, that's not what I wanted to point out. I wanted to point out this right here. This is a subtraction on RSP, so that's where we're making room in the stack. And it turns out that this is where we're passing the address of A, the address of B inside of F, that's where we're computing the address of B. Relative to the stack pointer, go up by 8. And that's consistent with what we saw here. So B is there. The stack pointer is there. This number is 8 more than that. Right? And then there's more stuff here before calling printf.